Thanks to Thamia for that great introduction to JWST. In this talk, I want to go slightly further back in Redshift. So we're not looking at the cosmic dawn, but rather we're looking at cosmic noon. And in particular, I want to talk about how JWST is revealing really exciting insights into the neutral gas reservoirs of galaxies at this epoch. So it all started at a collaboration meeting in January. We were looking through the newly reduced data, trying to see if there was something we could propose for cycle 2 follow-up. And suddenly we saw something really unexpected, which was these really strong sodium D absorption lines in galaxies at redshift 2, massive galaxies. And about 70% of these are actually blue shifted, which reveals neutral gas outflows from these systems. Now, this was completely unexpected. It was not in our proposal at all. And over the next 10 minutes, I hope I can convince you that this discovery is both exciting and important for our understanding of galaxy evolution. So astronomers have long known that galaxies transition from actively star forming to quiescent, and this process is broadly known as star formation quenching. However, we have very little understanding of the actual physical mechanisms that drive this transformation. Over the past decade or so, there has been a lot of attention put towards outflows as a potential quenching mechanism. These spectacular phenomena are triggered when processes like supernova explosions or black hole accretion deposit large amounts of energy into the surrounding gas, and then this can unbind gas from the galaxy and propel it out into the halo or even beyond. Now, we know that outflows contain cold gas, and cold gas is also the fuel for star formation. So if these outflows are powerful enough, then it is possible that they could remove all the fuel for star formation and therefore cause quenching. Of course, the big question is, are real outflows in nature actually powerful enough that they can remove this much gas that they can quench star formation? A key avenue to address this question over the last decade has been to study galaxies during the peak epoch of star formation and black hole growth. This is around a redshift of 1 to 3. This period is particularly important because it is when most stars in the universe formed, and that means that it's an important era to study if we want to understand the properties, the processes that shaped the properties of present-day massive galaxies. And also, it's the time when the rate of energy injection by star formation and black hole accretion peaked. And this means we also expect outflows to be most prevalent during this epoch. Now, there have been many examples of studies finding individual examples of powerful outflows with very large mass outflow rates that can surely eject their entire molecular gas reservoirs within timescales of a few 100 million years. The catch is that most of these are in quasar host galaxies or host galaxies of relatively luminous AGN. We know that rapid AGN accretion is a short phase in the life of the galaxy, and so a big open question has been whether these powerful outflows are actually common enough that they can impact the properties of the galaxy population as a whole. To try to address this, recently there have been several large near-infrared galaxy surveys that have attempted to constrain the incidence and average properties of outflows from normal main sequence galaxies at this epochs. And what these surveys have typically been finding is that actually these outflows seem to eject gas significantly slower than it is consumed by star formation. Here, this is just the mass loading factor, which is the ratio of the mass outflow rate to the star formation rate. And you see that we are getting values significantly below 1. So this seems to suggest that maybe outflows are actually not the main quenching mechanism that we think they could be. However, there is a key caveat, which is that most of our understanding of outflows comes only from observations of rest frame optical emission lines, and this probes ionized gas. Now, we know that outflows contain gas at a range of temperatures and densities, from cold molecular gas all the way to hot X-ray emitting gas. Unfortunately, we have very little understanding of how the outflowing mass is distributed between different gas phases. There have been some statistical studies at low redshift trying to constrain the outflow mass budget. And here I just wanted to highlight this study from the MANGA survey. On the x-axis, they show the outflow rate in ionized gas, and on the y-axis, the outflow rate in neutral gas. And this black line is the one-to-one line. So essentially what they're finding is that the neutral gas outflow rates are like 15 to 60 times higher than the ionized gas outflow rates. And if this is also true at high redshift, then this could completely change our understanding of the importance of ejective feedback. Now, unfortunately, we haven't been able to do these kind of studies at high redshift before, because this neutral outflow rate here is based on measurements of the sodium deabsorption line, and we need to be able to detect the rest frame optical stellar continuum of galaxies. And prior to JWST, this just wasn't possible for a significant sample of galaxies at this redshift. Of course, we've heard that JWST has completely changed the realms of possibilities, and in this case, it has made it possible to detect stellar continuum emission for a significant sample of normal galaxies at cosmic noon. So I'm part of a JWST Cycle 1 medium program called BlueJ, which got slid spectra of around 150 galaxies at cosmic noon across a wide range of stellar masses. Now, the most important, unique aspect of this survey is that it's designed to study stellar continuum, and this means it's one of the deepest data sets to be obtained in Cycle 1. Here you can just see an example of one of our spectra, and the data quality are amazing. And in particular, I want to draw your attention to this Balmer series region, where you can see that we have really good constraints on the stellar population properties in these galaxies from the Balmer absorption lines. So as I mentioned earlier, one of the first things that we saw when looking at this data set was these strong sodium deabsorption lines in quite a large number of galaxies from our sample. In this plot here, each of the panels is showing an absorption detected in a single galaxy, and the orange curves actually show the best fit stellar population models. So this absorption is much, much stronger than expected from the stellar populations alone. And we also have another piece of evidence to suggest that it's not from stellar absorption, which is the fact that in all of these cases, the centroid of the absorption is offset by at least 80 kilometers per second, and in some cases up to 600 kilometers per second. So here the colored boxes show the direction of the velocity shift. So 70% of these are actually blue shifted, and this is an unambiguous signature of neutral gas outflows. So here you can see where our detections are located in the stellar mass specific star formation rate plane. So the majority or all of these outflows are in galaxies above 10 to the 10 solar masses. And this is also seen in the local universe, this kind of mass threshold. And it's probably because you need a significant amount of dust to be able to shield the sodium atoms against ionization, because the ionization potential is only 5 eV. Now, interestingly, our detections span 4 orders of magnitude in specific star formation rate or more. They cover, the high envelope of the star forming main sequence all the way down to galaxies with very, very low star formation rates. One thing that's interesting to consider is whether the star forming galaxies and the quiescent galaxies have different absorption properties. I don't have time to go into this in a lot of detail, but we find that star forming galaxies and quiescent galaxies seem to show similar amounts of neutral gas. The absorption profiles have a similar depth in both cases. However, the gas seems to be moving faster away from the star forming galaxies. That is, the star forming galaxies have higher outflow velocities. And so one potential interpretation of this is that perhaps the sodium deabsorption observed in the quiescent galaxies is actually tracing gas ejected in previous powerful outflow episodes that were triggered while the galaxies were still star forming. And since the gas has been ejected, it moves through the halo and gradually slows down. But this is one possibility, but there are many others. So finally, the $1 million question is, are these neutral outflows actually an important source of ejective feedback? Now, unfortunately, this is not the data set that you really want to answer that question. It was not designed for kinematic analysis. As I mentioned, we didn't really expect this, and we only have a spectral resolution R of 1,000, which means that in some cases, the line profiles are spectrally unresolved. I did some crude back of the envelope, like mass outflow rate calculations, and at the order of magnitude level, they seem to be similar to the ionized outflow rates for galaxies at similar stellar mass and redshift. However, if we want to really be able to properly do an outflow mass budget for ionized and neutral gas at cosmic noon, then we need higher spectral resolution observations of both the ionized gas emission lines and the absorption lines for this sample. And I applied for JWST follow-up observations at RF 2700. Unfortunately, our cycle 2 proposal just missed out on being accepted, but hopefully in cycle 3, we'll be able to get some exciting data to address this question. So thank you very much.